Imagine the most terrifying object in the universe, a black hole. A cosmic abyss that swallows everything, light, matter, even time itself. A place where our understanding of physics collapses, where nothing can escape once it crosses the point of no return. The black hole is not just an object, it is a concept that defies logic and teeters on the edge of imagination. But what if we've been wrong? What if, instead of a monstrous singularity at its heart, the black hole is hiding a secret, an imposter, equally powerful, equally strange, but profoundly different? Welcome to the world of Gravastars, short for gravitational vacuum stars. These mysterious cosmic entities could be the black hole's twin, an alternative ending to a dying star, and a possible solution to some of physics' deepest problems. In this video, we'll journey through the science of gravastars. We'll explore how they might form, how they differ from black holes, and why they might just hold the key to a more complete understanding of the universe. Strap in, because this journey will take us to the limits of space, time, and reality itself. To understand gravastars, we first need to understand what they're meant to replace: black holes. According to Einstein's theory of general relativity, when a massive star exhausts its fuel, its own gravity causes it to collapse. If the mass is great enough, nothing can stop this collapse. The core shrinks to an infinitely dense point known as a singularity, surrounded by an event horizon, the boundary beyond which nothing can escape. Black holes are strange and terrifying, but they're also very real. We've observed their effects on nearby stars. We've detected gravitational waves from their collisions. And in 2019, the Event Horizon Telescope captured the first image of a black hole's shadow. But despite these observations, black holes remain deeply mysterious. At their core lies a paradox: the singularity, a point of infinite density where our laws of physics break down. It's a mathematical monster that tells us we're missing something fundamental. Add to that the information paradox, where information that falls into a black hole appears to be lost forever, violating quantum mechanics, and it becomes clear: black holes, as we understand them, can't be the full story. Enter the Gravastar. Proposed in 2001 by physicists Pao Mazur and Emil Mottola, the Gravastar is a radical alternative to black holes. Instead of forming a singularity, the collapsing star transitions into a new phase of matter, an exotic state dominated by vacuum energy. In this model, the Gravastar consists of three layers: core, a sphere of dark energy, or vacuum energy exerting negative pressure; shell, a thin layer of ultra-dense exotic matter acting like a membrane; exterior, from the outside indistinguishable from a black hole. Same mass, same gravitational pull. The Gravastar doesn't have a singularity. It doesn't have an event horizon in the traditional sense. Instead, the ultra-dense shell reflects anything trying to get in. This means it doesn't violate quantum mechanics. It doesn't destroy information. It's stable, elegant, and theoretically possible. In quantum field theory, even the vacuum of space isn't truly empty. It's seized with virtual particles popping in and out of existence. This residual energy, the zero-point energy of space, is vacuum energy. In the Gravastar model, the collapsing star doesn't form a singularity. Instead, it transforms into a bubble of this vacuum energy. The result is a stable object, supported by the negative pressure of the vacuum. This pressure pushes outward, counteracting the force of gravity. It's as if the universe has a way to avoid tearing itself apart. Instead of creating a singularity, it creates a kind of cosmic soap bubble. But to make this work, we need exotic matter, material with negative energy density, which has never been observed in the lab. This is one of the Gravastar's major criticisms. It depends on a form of matter we're not sure exists. So if Gravastars exist, how could we find one? That's the tricky part. From the outside, a Gravastar and a black hole behave almost identically. They bend light the same way. They create the same gravitational waves. Even their shadows, like the one captured by the Event Horizon Telescope, would be nearly identical. But there is one potential clue: gravitational wave echoes. When two black holes collide, they send ripples through space-time. These ripples, gravitational waves, ring out like a bell. If gravastars exist, their solid shell might create an echo, a faint secondary signal after the main wave. Some scientists have claimed to detect these echoes, but the evidence is still debated. With more sensitive detectors in the future, we might be able to tell the difference. For now, it remains one of the most tantalizing possibilities in astrophysics. If gravastars are real, the implications are enormous. First, they solve the information paradox. Since gravastars don't destroy information, they respect the laws of quantum mechanics. Second, they avoid the singularity problem. Instead of a breakdown of physics, they offer a new state of matter. Gravastars might also be connected to dark energy, the mysterious force driving the expansion of the universe. If gravastars are made of vacuum energy, they might offer insights into the nature of dark energy itself. They could even point the way to a quantum theory of gravity, a long-sought goal of modern physics. By studying gravastars, we might find clues to how gravity and quantum mechanics fit together. Not everyone is convinced. Critics argue that gravastars are too speculative, that the exotic matter they require may not exist. Others point out that without observational evidence, gravastars remain in the realm of theory. But even skeptics admit, the black hole paradoxes are real. If gravastars aren't the answer, then we still need one. Whether it's gravastars, wormholes, or something else entirely, the mystery remains. Meanwhile, researchers continue to refine their models. Simulations grow more complex. Observatories grow more sensitive. The line between science fiction and science is slowly fading. In the coming decades, new telescopes and gravitational wave detectors will open up the universe like never before. Missions like LISA, the Laser Interferometer Space Antenna, will detect gravitational waves from deep space with precision we've never seen before. If gravastars exist, LISA might hear their echoes. We might even spot one through careful analysis of black hole shadows. Or perhaps we'll find something even stranger, something no one has predicted. Whatever we find, one thing is certain. The universe is more mysterious than we ever imagined, and gravastars are a shining example of that mystery. Gravastars challenge everything we think we know about gravity, space, and the life of stars. They might be the elegant solution to our deepest problems, or they might be a cosmic red herring. But in either case, they force us to ask the big questions. What happens when a star dies? What is the true nature of space and time? Can we ever unify gravity with quantum mechanics? In the end, gravastars remind us that science is not just about answers. It's about curiosity, about looking up at the night sky and wondering, what if? If you enjoyed this journey into the strange and beautiful universe, don't forget to like, share, and subscribe. And remember, in the vast, mysterious cosmos, even the wildest ideas might one day prove to be true. Thanks for watching.